So as we mentioned in the notes, the F distribution represents the distribution of possible F ratios that we would get if we're collecting data from samples that actually each share the same population mean. So you can kind of think about it as if we were just taking 3 samples from the same distribution, or we're taking three or more samples from different distributions, but those distributions all share the same mean. Um, so we're going to kind of demonstrate what that means. So right here, what I'm going to do is simulate a kind of a random data set. I'm just going to take some uniform distribution values. So I'm going to actually create a population of about 100,000 data points here, uniformly distributed from 0 to 10. So in case you're wondering what that looks like, it's going to look something like this here. So I just simulated some giant population, uniformly distributed from 0 to 10. It honestly doesn't matter where these come from. It doesn't matter what the values are or how they're distributed. It's just some population for me to work with. And I'm going to take random samples from this population, and I'm just going to do it of size 20. Again, the sample size doesn't particularly matter that much here, but I'm just going to take 3 different samples of size 20 from this population that I just kind of generated there. So then I'm going to do that, and then I'm also going to throw them into a data frame. And now I'm going to plot what my 3 samples look like. So we can kind of see how much variability there is between these 3 samples. And you can see that just by random chance variation alone, I do have a little bit of difference between these samples, right? So chance variation tells us that we expect our sample means to be different, especially when our sample sizes are not particularly big. So that would certainly apply here. I have sample sizes of 20. If I were to make these larger samples, hopefully they'd be a little bit more homogeneous, but this is what happens by chance variation. We get some difference. And then I can calculate an ANOVA. So I can run an ANOVA to see how compatible these samples are with the idea that they all come from populations sharing the same mean, which is actually true in this case. And I get an F ratio of 1.73. So that means that my between variance is 1.73 times higher than the average within variance. So it's a little bit high, but not particularly unusually high. And I could do the same process again with another set of random samples, and they may or may not be the same distance apart. They might be closer. So here it looks like my samples are a lot more centered, and I actually get an F ratio that's quite small at 0.17. So that just kind of represents this idea of what I'm doing. An F distribution would be if I just repeated this process many times and recorded all the different F ratios that I got just by random chance variation. So that's actually what I'm going to do down here. I'm going to get this running here because it will take a little bit of time. But what this code's going to do is it's actually going to simulate this process above 10,000 times. So I'm going to take 10,000 sets of random samples from the same population, so again from the same population above, and I'm going to run an ANOVA and record the F statistic. And so I'm going to do that 10,000 times and then create a density curve of all my different F ratios from this random sampling process. And that distribution of F ratios is what we call the F distribution. And then one note here is that the F distribution does depend on how many samples I take, so how many groups I'm comparing. And it does also depend on the sample size that I take for each group. So a couple things to keep in mind. The more groups you have, the more spread out the F distribution is going to be. The more you're going to see some higher F ratios by random chance. Also, the smaller the sample size you take, again, the larger the F ratios can be when you have small samples. All right, so I paused, inserted again there. So here's what I got. And as you can see, most of my F ratios are kind of around this 0 to 1, 2 range. I do get some F ratios a little bit higher by random chance, but obviously just not very often. So when we ever do an ANOVA with 3 groups, and we don't already know that they're coming from the same distribution, our F ratio kind of tells us how compatible our results are with the null hypothesis that these however many groups all come from populations with the same mean. Because if we're getting an F ratio out here, it's telling us that that's pretty incompatible, that this is a pretty unusual result if that's true. If we're getting an F ratio more over here, it's saying, well, this is something that would happen by random chance. It's not particularly unusual.